Good morning, everyone. We'll be starting the webinar in about 10 minutes. So we'll get back on and start promptly at 11 o'clock.
Okay, folks, about 5 more minutes and we'll be getting started, starting promptly at 11 o'clock. Thanks very much.
Good morning, everyone, and welcome to the Reliability Solution for Thermal Power Plants, hosted by A.W. Chesterton. My name is Hisham Sadi. I'm the Global Product Manager for the ARC Efficiency and Protective Coatings Group. Co-hosting the webinar with me is Steve Bowditch, Global Market Development Manager, also for the ARC Efficiency and Protective Coatings Group. So today we will discuss the key issues facing the Demineralization systems in thermal power plants. Just before we get started though, just a few housekeeping notes. If you have any questions along the way in the webinar, there's a questions box that you can type them into. If it's something that we can answer quickly, we will do so on the spot. If it's something that requires a longer, in-depth answer, we will get back to it at the end of the webinar. Also, there are a few handouts in the Handouts tab that you can download for your review, and you can look through them later on. At the end of the webinar, we will put a link for a short survey. If you could please take that survey, it's only a few questions. Let us know how we did today, what you like, what you didn't like, and how we can improve in future webinars. And lastly, a recording of this webinar will be available and will be emailed to you later on this week. So with that, let's get started. So today we will take a look at identifying critical systems in the Demineralization process. As we do that, we will look at the raw water filtration, we'll look at the cationic bed, we'll look at the degasifiers, we'll look at the anionic beds. We'll also review mixed bed polishers. Not all power plants have those, but if you have them, we'll also be reviewing those, so you can take a look at that. We'll also review the acid and alkali regeneration systems. After that, we'll look at principal forms of corrosion. We'll discuss root cause analysis of all the different types of corrosion that we see in Demineralization systems, and we'll present a few options for resolution, what could be used to solve these corrosion issues. Just before we get started, let's take a look at some statistics. A NACE 2016 study estimates the global cost of corrosion at $2.5 trillion annually. That's equivalent to 3.4% of the global GDP. Now, using best practice technology that's available today, it is estimated that savings could be realized in the area of 15 to 35%. That's $375 to $875 billion annually, roughly. If we look at the United States alone, the cost of corrosion in the power generation sector, between power generation and transmission, was $6.9 billion. Using the same factor here of using best practice methods, if proper corrosion protection is applied, that could result in savings between $1 and $2.4 billion annually. Now, before we get started and look into this whole process, Steve, you've been doing this for quite a few years now. I think 40 years or so you've been in the industry?
About 35, 40 years, yes.
35, 40 years. Before we get started, can you give us a brief caption of why it's important to have pure water and to go through the demineralization process?
Yeah, I'd be happy to. Demineralization is one of the critical areas in any thermal steam-fired power plant, whether it be fossil, oil, or nuclear. Demineralization is intended to provide high-purity water that can be circulated through the condensate loop, going through the boiler, into the turbine, back down into the condenser, and then back through the condensate system. The purity of the water is extremely important for a couple of reasons. One, to remove the potential effects for corrosion that might occur within the systems, as also reducing scaling, but it's also extremely important to improve the actual thermal capability of the power plant itself. So the Demineralization plant is an extremely important portion of the plant. It's an area of the plant that sometimes gets overlooked as far as the areas for corrosion prevention and protection, and it's an area that we want to bring some attention to today.
Thank you, Steve. So as we look at the Demineralization process, we're going to start with filtered water entering into the cation exchange. So we've already used filters to remove the suspended particulates, the large particulates, and now we're strictly looking at the cationic, from the cationic process on, from the cationic bed on. So what's the purpose of the cation exchange bed? The cation exchange bed is removing our cations or our positive ions. These are things such as our sodiums, our dissolved salts. Once past the cationic bed, the water continues on to the degasifier. That's where all the dissolved CO2 is removed from the water. It then continues on. We go to our anionic bed, where we're removing our anions or our negative ions, such as our chlorides. And now after the cationic bed and the anionic bed, we're using testing to see what's going on, to figure out if they've been used up. So the resins over time get saturated as they pick up ions from the water, and they have to be regenerated. So after the cationic bed, what we're testing for is we're testing for dissolved salts in the water, and after the anionic bed, we're testing for conductivity. Those two measurements give us a reference of the well-being of the resin itself, of the resin media, and once it indicates that it needs to be regenerated, it sends a signal for the system to be regenerated. And that's used, we use acids or alkalis to go in and regenerate those systems. And that typically requires a shutdown of the process to go in and clean out the ions. So you either acid wash it or wash it with an alkali, and then we decontaminate the tanks. All the slurry or the water is discharged, and then the process could continue again. Past the anionic bed, we get to the mixed bed filter or the polisher. Now this is only used in certain power plants that require ultra high purity water, and that's where we're using both cations and anionic resins, and the water is circulated between the two. What this is going to give us, it's going to capture anything that was missed in the first two stages between the cation and the anions. So that's going to scrub off any remaining ions that are left in the water. Once we go past that, the water is sent to the Demin water storage tank, where it's stored for processing. So if we look at key issues that are associated with the cation and anion demineralization. So we want to have corrosion avoidance in the steam and condensate loops. So as we discussed before, we have the degasifier, and the degasifier is removing the dissolved CO2. This dissolved CO2, once it's in the condensate loops, it reacts with water, forming carbonic acid. As the carbonic acid deposits on turbine blades, for example, as you see in this picture here, it will cause corrosion on the system. So you have your steel, your turbine blades could be getting corroded due to dissolved oxygen, dissolved carbon dioxide reacting with water, forming carbonic acid that's deposited on the turbine blades. And as that passivated layer gets removed, more carbonic acids gets deposited, and so the process continues on and causing further and further corrosion.
Another area, Hisham, that we want to bring up is if the demin process is not functioning properly and you are not stripping out some of the chloride anions from the system, then those chloride ions can also be corrosion initiators in these process areas. So in the turbines, in the feed water heat exchangers, in high temperature areas, particularly high temperature chlorides tend to be highly corrosive. So it's extremely important that the demin process remove the chloride or the negative, the anionic systems.
Thank you. Also, another area where we have to look at is to minimize scale formation on the boiler tubes. So what happens is scale forms inside the boiler tubes. As we flash out water, as water is evaporated and turned into steam, the water is only turning into steam. Any dissolved salts that are remaining in the water, that's going to form scale inside the tubes. And what that does, it reduces the efficiency of the tubes. It could cause overpressurization due to the reduction of the diameter of the tubes themselves, which will in turn create localized heat spots, and the localized heat spots will fatigue the metal, which could lead to rupture of the tube, which is very dangerous, could be a life-threatening situation. Also, the chemical containment areas are under constant attack. That's under constant attack from leaky valves, fittings, anywhere in the loading and unloading of chemicals. There could be chemicals that are coming in contact with the concrete. There could be chemicals getting in contact with different types of metals that could be causing all that contamination. It could be doing significant corrosion to all those areas there. Your pump bases, your drains, your floor drains, your sump pumps, all that could be getting corroded due to chemical spills in those areas. And last but not least, we need to look at the water purity. After we go through the demineralization of the water has been stripped of all those ions are in it, either positive or negative ions. Water by its nature wants to gain those ions back. So it's going to look for sources to obtain ions. And one of the best sources to get ions from are metals, steels, carbon steels. The water is going to go to the steel and pull those ions out of the steel. Steel by itself is not very protective of the ions that are present in it, so it gives up those ions, and that's what corrosion is. It's metal oxides, it's iron crystals forming back to iron oxides.
So the issue that we want to bring up here is that while you go through this exhaustive process and procedure at some cost to remove those anions and cations from the water, that water wants to recoup and regain those systems, so it's going to want to leach them out of unprotected metal, uncoated metal.
Absolutely.
That's the issue that we're talking about. Okay, thanks.
So now that we've reviewed the Demineralization process, let's take a quick look at the typical forms of corrosions that are encountered in the Demineralization system. So we have scaling corrosion, pitting corrosion. We could also have chemical attack due to oxidation of the steel, and chemical attack which is neutralization, that's mainly predominantly associated with concrete.
Okay.
So if we look at scaling is the precipitation of mineral salts present in water. So like we mentioned earlier, as the water flashes and turns into steam, the dissolved salts that are left behind deposit on the inside of the boiler tubes. What that does, it forms a hard calcium-like deposit on the inside of your tubes, reducing the diameter of the tube, which in turn leads to overpressurization of the tube, creating localized heat spots. Those localized heat spots overstress the metal in areas versus others, and those areas that are stressed with that added temperature, the extra heat that's in there, those are going to be potential failure points. Now, to remove scale that's formed on the inside of your tubes, it could be removed via mechanical means, or most commonly it's typically done via acid washes, either hydrochloric, sulfamic, or citric acid. It's no different than when you have to go and clean your coffee maker at home. You look in your coffee maker and you see these white powdery substances. That's scale forming on the inside of the coffee maker. And what do? We run vinegar through the coffee maker.
What is vinegar?
Citric acid.
Or acetic acid. Right. So acetic acid will remove those calcareous deposits, and you have clean coffee again.
Clean coffee. You can enjoy your cup of coffee after that.
Obviously, you don't want your coffee pot exploding either.
I would hope not.
Okay.
So pitting corrosions. So pitting corrosion, it's due to the removal of a passivated oxide layer in a local spot. So what happens is, as you have corrosion happening sometimes uniformly across the surface, the removal of the corrosion from a certain spot creates a difference between an anodic and a cathodic region. So the pits form into mini galvanic cells where the rate of corrosion on the inside of the cell, on the bottom of the pit, is higher than the top of the pit. That's because the pH itself, the acidity, is higher in the bottom of the pits. So as the acidity increases in the bottom of the pit compared to the surface, what that does, it creates a mini galvanic cell where ions are being removed at a much faster rate at the bottom of the pit than at the top. So the pit tends to get deeper in the metal rather than expand horizontally across the surface more uniformly. And if left untreated, those pitting corrosion cells will end up eating right through the metal, causing failure.
So if corrosion is occurring in a pit, the rate of corrosion is faster at the bottom of the pit than at the top of the pit, and that's due to the fact that the acidic condition there is an environment that's more conducive to corrosion because ions are transferring at a faster rate in that electrically conductive low pH solution at the bottom of the pit?
Absolutely.
Okay, so if there's a way one way that could be in theory to resolve pitting corrosion is if you're constantly flushing that pit out and removing that low pH contaminant, that would be a process issue that could potentially remove pitting corrosion as an effect.
That could be done that way, yes.
Practically speaking, how to do that is another issue.
Yes.
Okay.
And also, the pits themselves cause more turbulent flow to happen, and the turbulent flow that occurs in the pits themselves, and as the water is going across, removes that passivated layer. And once that passivated layer is removed, another one needs to form, and that's how the process continues and causes rapid corrosion also.
Okay.
Another form of corrosion that's typically experienced in demon systems is oxidation. So, like we discussed earlier, the alkalinity in the feed water breaks down in the boiler, and the CO2 is released into the steam loop. The CO2 reacts with water, forming carbonic acid. This carbonic acid gets deposited on the metal surfaces, such as in the turbine blades, and that causes corrosion itself. And like we previously mentioned, as turbulent flow passes over those areas, the passivated layer is removed, and as more carbonic acid gets deposited, you see more loss, more corrosion occurring. That's when we have an unwanted acid forming. But in a lot of our processes, like we just mentioned, we intentionally add in acids and alkalis into the system to clean them. So anytime we add those acids in, those low concentration acids are attacking the metal, they're causing it to oxidize, they're causing corrosion. Okay. Another form of corrosion that we experience, it's chemical attack neutralization. So this is predominantly happens with concrete. So if we look at concrete is a mixture of Portland cement, sand, water, and aggregate. Portland cement is made up of about 65% calcium hydroxide. Calcium hydroxide is basic. As you have acids coming into contact with it, they react. No different than, let's say, adding baking soda and vinegar, mixing them together. That violent reaction that occurs between the two, that's exactly what's happening in concrete when it comes in contact with an acid. The acid dissolves the calcium hydroxide and turns it into calcium sulfate, which is a water-soluble salt. So it turns into calcium sulfate and water. And as you have water flowing, it's water-soluble. That gets washed away. Essentially what you're doing is you are breaking down the binder that's holding the concrete together. As this binder is broken down, the concrete starts to fall apart. Once first you start losing your aggregate, then you start losing your sand, eventually start exposing your metal rebar. Once exposed to corrosion to the environment, the metal rebar, which was initially protected by the basic concrete, the concrete that's has a basic pH, starts to expand. The expansion of this rebar causes cracking, which leads to further penetration of acids into the concrete, progressing the failure of the concrete.
Yeah, I personally have experience working in a demineralization process in a power plant where the floor drains were so heavily attacked that by the time I finished trying to neutralize the acidified concrete, there was no concrete left, and I was actually down into the soil. So I had gone through about 12 inches of concrete, and I had to excavate about another 18 inches of soil before I got to a neutral pH. So that's the, if the attack occurs, and it occurs over years and years, that can be quite pronounced and can add to groundwater or soil remediation or groundwater remediation if you're dealing with acids.
Absolutely.
So there is an environmental issue as well associated with these this type of attack.
Not to mention the added environmental cost of remediation.
Exactly.
So now that we've looked at the different types of corrosion, let's take a look at the most problematic areas and the types of corrosion that's typically experienced in them. So as you can see from this table, we have very limited materials of construction that are used. So typically we're either dealing with steel, stainless steel, concrete, and very occasionally poly inserts. And the modes of failure that or corrosion that's experienced is typically either erosion corrosion, chemical attack, or neutralization. So if you look at this table, you can see what you have in your plant and what the type of corrosion that's experienced in every single area in the system. So how can we mitigate the effects of corrosion? The next few slides will discuss solutions to mitigate the effects of corrosion. So we have a few different methods that we can mitigate the effect. We can look at materials of construction. So ideally, if we can build everything out of gold or platinum, they're very unreactive metals, and that would be perfect. We won't have to use any form of protection. But that's not possible, obviously, for cost constraints. So we have to look at different things to address. So our materials of construction in the systems are typically either carbon steel or stainless steel. So next we have to look at our process chemistries. So the process chemistry, you want to keep the process chemistry in line with the design criteria of the system. And that's done via measuring pH and conductivity, like we mentioned earlier. So after your cation, you're measuring your pH. After your anion, you're measuring your conductivity. You're making sure the process chemistry across the whole system remains in check, so that way you're not adding either increased ions or anions, cations or anions in the system. Another potential solution is sheet rubber linings. So you can coat the inside of vessels with the sheet rubber, or we can use liquid epoxy linings or solutions. So if we look at rubber linings, so the advantage of rubber lining, it provides a continuous film which reduces the chances of porosity and protects the metal. The disadvantages, though, as you can see in the picture on the right-hand side, there are many seams when coating a tank, for example, when applying sheet rubber gasketing to a tank. The sheet rubber has all these seams, and every single one of these seams ends up being a potential failure point where our leak paths could generate at the seam and travel behind the rubber, causing a failure anywhere behind that sheet of rubber. It requires long shutdowns. So if it requires longer shutdowns to install, specialized equipment to remove and install it. So you also have to come in and do surface preparation behind it also. So you can't apply it to a unclean surface, you're adhering it to the metal, so you have to do significant surface preparation. As you can see, as we mentioned before, you have leak paths in the rubber. And any one of those seams could be a potential leak path. And what that does, as the water or the acid solutions come behind the rubber, it starts corroding the metal behind, which is, it's a hidden problem until you see blistering happening in the rubber. And once you see this blistering, as you can see in this picture right here, several areas are blistered. But that doesn't necessarily mean that's where the failure occurred. The failure could have started several feet away at a seam, and then it just traveled to that area, and that's where the corrosion began. We have this one right here. You can see a close-up of what the bubbles look like, or in system. Poke one of those, and you'll see water come right out, gushing right out of these blisters there.
And you'll also see pitting typically on the backside of the steel.
Absolutely.
And that's one of the issues when you're repairing a rubber lining is the rubber lining has to be applied to a fared smooth surface. So if you have pitting occurring on the steel, that requires them to do weld overlay on those pitted regions and then grind everything flush. So there's a hot work issue, there's a fire watch, there's extended time, there's also the potential of sparks and flames damaging adjacent rubber areas. So whenever you have damage to a rubber lining, the repairability is not the easiest thing.
And lastly, rubber gets brittle over time. As the rubber oxidizes, it becomes brittle. As you can see in this picture, there's mini cracks that form in the rubber, which in themselves are small pathways for additional water or acids or alkalis to penetrate behind the rubber itself and causing further corrosion. Just think of it as if you have like a rubber garden hose that you leave outside in the sun, how it becomes brittle and starts to crack. That's oxidation. That's exactly what happens to the rubber on the inside of the tanks as well. And we also have liquid epoxy solutions. So liquid epoxy solutions, the advantage to using them, they have superior corrosion protection. They're relatively easy to install. You can install them by either brushing them on, rolling them on, or applying them via either airless or pluricomponent spray systems. They're typically fast cure systems where their cure could be anywhere between a few hours to up to 7 days, depending on the chemistry and the environmental conditions that you're applying to. A few disadvantages, however, is they require surface preparation, just like the rubber does. Improper mixing or application could lead to premature failure. So if your environmental conditions aren't right for applying a coating, that could lead to a premature failure. If it's not mixed to ratio in two-component epoxies, that could also lead to a failure. And you could potentially have also residual leaching or contamination of the demon water. So if something is not mixed properly
or cured properly,
you could have components of the epoxy itself leach back into the demineralized water. Like we said earlier, the water wants to attract ions, and it could start pulling things out of the epoxy if it's not mixed properly or applied properly or cured properly. So a few key takeaways before we wrap up. Corrosion in the demon system could be costly and even dangerous, could be life-threatening if boiler tubes explode. The cation removes our positive ions, our dissolved salts such as our sodiums. Our anion is removing our chlorides or our negative ions. Our mixed beds are removing both cation and anion in that stage. Different forms of corrosion that happen. We have scaling, which is the precipitation of mineral salts.
Which could be not just your sodium salts, but also your potassiums, your magnesiums, all of
calciums, anything.
Okay, so any of your salt compounds that can be found in your water. And remember, you're typically taking raw water. So this is city water. This is coming out of the tap. That water is not going through a reverse osmosis purification system. It's typically going through a chlorination process. It's going through a suspended solids process, and that's it.
That's it. We have pitting corrosion. Like we discussed, we're forming mini galvanic cells that are causing corrosion into the metal. Chemical attack or oxidation of the steel. This is where it's happening more uniformly across the surface. And the chemical attack in the form of neutralization of the concrete, where we have acid in contact with the concrete itself, dissolving components of the Portland cement, making them water soluble and destroying the concrete that way. It's very important to keep in mind the materials of construction in each area and to choose the materials of construction that are best fit for the application. Process chemistry, maintaining it within design parameters. We can't stress that enough, making sure that you're not exceeding your pH levels that are recommended for the systems, or the conductivity, so you're removing your your positive and negative ions.
Just as a point of clarification or emphasis here, in the nuclear industry, particularly in the nuclear industry, process water chemistry is one of the most important areas of the plant. And if the process chemistry, if the water chemistry is not correct in the nuclear power plant, that can bring a plant offline. So they will very quickly respond and react to issues about process disruptions in their system if they notice a high level of conductivity coming off of the anion, or a low pH coming off of the cation, or off the mixed bed polishers. That will impact plant productivity, and they may take the plant offline to correct those issues. So this is an extremely important area. Obviously, it's more critical in the nuclear industry, particularly with your pressurized water reactors, because that condensate is a radioactive fluid, so they're very concerned about that. Okay, we have a questionnaire here from Ismail. Would you please kindly comment on high temperature corrosion in boilers as well, and how it could be tackled? Well, there's an issue there, particularly in high temperature corrosion, and high temperature corrosion in the boilers is operating in somewhere north of 700 to 800 degrees Fahrenheit. So you're normally well beyond the effect of any kind of lining system, organic lining system, like any of the rubbers or liquid epoxies that we're talking about. At those temperatures, you're going to have to address it with typically some type of thermal sprayed material, whether that be a thermal sprayed metal or thermal sprayed ceramic systems that can be applied. Anything that you can to reduce any potential risk for chlorides, because chlorides become particularly aggressive at elevated temperatures. So anything you can do to remove those chlorides to maintain that process water chemistry is also extremely important. But within the boiler itself, the most common forms of corrosion protection are the removal of dissolved oxygen and dissolved CO2, and the utilization of thermal spray type coating systems for corrosion protection or erosion protection.
All right. Thank you, Steve. Also, like we mentioned, rubber liners are used to protect storage areas, storage vessels, tanks, and liquid epoxies, either 1-part or 2-part co-reactive epoxies. So we didn't mention that earlier, we didn't go into detail, but you have typically 2 types of epoxies. Your 1-part epoxy solvent-based systems that are applied, and you have 2-part epoxy systems that are mixed together. You have a resin and a curing agent that get mixed together, they're co-reactive, and then they're applied. So there are advantages and disadvantages to both.
What are some of the advantages that you would see with a 1-part solvent-based epoxy?
So you don't have a limited work time for a 1-part system, so you can apply it. The solvent evaporates out of it. You can go back and recoat it. You don't have to really stick to a specific overcoat window. As the second coat, the solvent in it dissolves that coat, and then they'll bond together the different coats. However, still a single coat system, solvent-based, are, as the name mentioned, they have a lot of solvents in them. So your wet film thickness is not what you're going to end up having as a dry film thickness. So if you have a system that's 50% solvent, you apply at 20 mils thick, let's say, you're left with 10 mils. 50% of that is going to be evaporated due to the solvent flashing out of the system. That's going to lead to shrinkage, and applying solvents in an enclosed environments, having all the PPE and ventilation, that's usually frowned upon by many.
Okay, so two areas to be concerned about with any kind of solvent-based system will be shrinkage, cure shrinkage, and then there's the issue about environmental concerns for the application from a safety issue regarding explosion and flammability.
Absolutely.
All right. Now the two-part systems, what is the two-part system? How does the two-part system address those 2 points as far as film shrinkage and also as far as environmental concerns in the work area?
Yeah. So two-part systems are either 100% solid or near 100% solid, so you have essentially no shrinkage. And since they don't contain any solvents in them, your wet film thickness will be the dry film thickness. So you apply your coating at 20 mils, it's going to stay at 20 mils. So that's the advantage of them. A slight disadvantage is now that you're mixing an A and a B, you have to keep in mind the working time of the epoxy and make sure you have it applied within the working time of the system itself, so you don't have it gel and then it won't be an effective coating, as it won't bind properly to the metal surface behind it.
Okay. All right. So what we're looking at from this point, hopefully, is an understanding and appreciation of how important it is to maintain proper process control and demineralization systems. Corrosion is present in these areas. We've identified the primary forms of corrosion and where they're most commonly seen. And we've identified some of the materials of construction process issues, as well as protective coating solutions that can be brought to bear to try and address some of that high cost of corrosion that we see in the industry. So as we wrap up this seminar, the intent is to make sure that everybody understands that demin is a critical part of any thermal power plant, that process control and process operation is extremely important as well, that there are acceptable, well-time tested, proven methods to address corrosion. The two most commonly used in these vessel systems are rubber linings and liquid applied epoxy-based coatings. Both of those have their pros and cons. Rubber lining systems have been in the market and lining vessels for 30 to 40 years. Typical lifespan of these coatings, depending upon the grade of the rubber, normally between 7 to 12 years would typically be a good life of rubber lining. Rubber lining gets to 10 to 15 years, 20 years, it's going to start to show signs of cracking. You might start to see advanced signs of blistering. And one of the most important things to remember about rubber lining is the ability to easily repair and patch rubber lining is nowhere near as easy as it is for liquid epoxy coatings. And yet both of these systems have been proven to provide, 10 to 15 year service life quite reliably.
With that, do we have any other questions? Anyone else, any questions or comments that they'd like to share with us?
As we said, this presentation it's been recorded, and all attendees will receive a link to view this again. And there will be a survey also in the, where's the survey going to be found? That'll be found in the chat room area?
Yes, it'll be in the chat box. We'll put a link in there. And if you can, please take that short survey, just a few questions. If you could let us know what you liked, what you didn't like,
yep,
how we can
and a couple better. We've also added in a couple of handouts that are available to you. One is our power guide, which gives an in-depth overview of the thermal power plant process areas, of which demineralization is one of them, and it identifies all of the solutions that Chesterton offers for those areas. And then specifically, we have a couple of case history applications for our protective coatings in the industry itself. And that's it, folks, from our end. So we'll be happy to take any questions. And if we don't see any questions, please take the chance to fill out the survey and let us know how we did, how we can do better. Okay, we have a quick question from Ulysses. After surface preparation, do you suggest the use of MEK? Do we have to wait some time before applying the coating? I think the question here is, after we've grit blasted the surface, do we suggest the use of a solvent to remove any dust residues from the surface? I would never recommend that, Ulysses, for the simple reason that you're in a confined space, and using a highly flammable solvent in that confined space is highly dangerous. So if you're looking to remove any blast residues, I would recommend using a vacuum system with a HEPA filter to remove any of your blast residues, and then use a clear piece of Scotch tape pressed onto the surface, removed from the surface, and pressed on a piece of clean white paper to determine how effective you are at removing blast residues. But do not use any type of flammable or explosive solvent, and it would be my desire that you not use any type of solvent in those confined areas. It's not good for the workers, and it's not good for the environment. All right, folks, that's going to wrap up our webinar for today. I thank you for your time, and I hope you all have a very productive week. For those of you who are in the Northeast, hang on tight. Mother Nature's coming back with one more nor'easter. There's one more question that came in from Ulysses. Okay. In the presentation attached, the solution includes this step, but thank you. Okay, thanks for that. Thank you very much, everybody.